Hey guys, this is GKCS. Today we have a very special guest with us, that is Karthik Arora. Karthik has a YouTube channel on algorithms and on computer programming. He's really good at computer programming and algorithms, and you should definitely check out his channel. It's in the link in the description. Karthik, are you ready to get challenged?
Definitely up for it.
This is the problem. Initially, we have a robot at position 0. Okay, and this is a 1D problem. So basically this is an integer line from negative infinity to positive infinity. You are at position 0, you are at the origin. What you need to do is you want to go as far right as possible or as far left as possible. Basically you want to get out of your house as much as possible. This is COVID times, so even for robots, I think what we need to do here is that firstly you have n instructions. Okay, each instruction is of type left or right and a particular amount x. So if you say left 50, then it means that if you're starting from 0, you go to minus 50.
Okay, fine. So that is the instruction. Okay.
Right. So now if you have the right instruction next, so this is instruction number 1, instruction number 2 is, let's say, write 25, then the cumulative of that gives you position minus 25. Okay, so you're just taking a robot and you're just moving forward according to the instructions. You have n instructions, so you will have, let's say, another right 30 which sends you to 5. You have a left 20 which sends you to minus 15. Right, you have a bunch of instructions, but your motivation is very clear. You want to go as far right or as far left as possible. What do you do? Amongst these n instructions, if you take this in an array, right, if you take these set of instructions as an array, you can remove a subset or rather a subarray from this array. Okay, so if I take an example, let's say I remove this part of the array. This is a subarray, right?
Okay.
Has been eliminated. Now I have this array. L50 sends me to minus 50. Then L20 sends me to minus 70, which is the maximum left I can go to. Right, and that is also, in terms of distance, it is a distance of 70, very far from the origin. I'm happy. This is the correct solution for this problem.
All right. So, okay, I think that makes sense. Actually, there are n instructions already given to the robot, and instruction is kind of like this. Hey, move to the right 10 steps or move to the left 25 steps. That is one.
Correct.
And my goal is to send it as far as possible from my house because of COVID, of course.
Yeah. You're going to go to Kumbh Mela soon.
Okay, fine. Sure. So I can delete any subarray of instructions is
Yes. So it has to be contiguous. You can't remove. You can't say that I want to remove 2 and 4, because that is not a contiguous block. So you can't say that please remove this and please remove this. Not a subsequence, but a subarray.
Got it. So okay, first thing what I would like to do is these instructions are a bit hard to interpret at the moment. Let me change the interpretation of the problem a little bit. Let's say L means left, so let's make it minus. So L50 becomes minus 50. And then R25 means towards the right, so that becomes plus 25.
Okay, I'm getting where you're coming from. This is your transformed subarray.
Yes, that's what I'm thinking of. And now the problem actually becomes that, okay, if I do not delete any subarray from this, then my displacement is going to be the sum of all these elements.
Yes.
Right. And I would either like my sum to be as large as possible, which means sending the robot to as right as possible, or I would like my sum to be as small, that means in the negative direction, as possible. So sending my robot to the left. Okay, I think that is making sense. So since this is a subarray problem,
You can try a brute force if you like.
yeah, exactly. Since this is a sub-array problem, I can try out all the subarrays.
Okay, so that would be like you'll have I think n into n plus 1 by 2 subarrays.
Right. Let's just take it n square.
N square. Okay, so n square subarrays, and for each subarray, how do you find the sum? Are you going to like do it brute force? That will be order n again over there. So order n cube is the absolute brute force solution, but it works.
Yeah, it will work because I'm like trying out, okay, what if I delete this subarray? Then what is the displacement? What if I delete some other subarray displacement? And among all these possible displacements, whichever is the like largest and the smallest, that means most negative and most positive. Among these two, whichever is like in greater in magnitude, that is my answer. So this n cubes works.
Yeah, no, you can make it much faster immediately. Can like maybe the audience will know about this. Which one would you use a data structure to quickly find a sum of every subarray?
Okay, so I can probably use prefix sums, of course.
Okay, prefix sums, order n square. Okay, now can we do better than this?
Okay, so I am thinking in two directions, right? Either send it to the left or send it to the right. For the sake of my simplicity, I'll try to think of sending the robot only to the right font.
Okay. So basically, you're trying to take you're trying to send it to the right, means make it as positive as possible. So the removed part will be as negative as possible. That's the intention, right?
Like previously, we were thinking about two directions, but now I'm focused on sending it only towards the right. So that makes sense. I would like to remove a subarray that is the most negative, because then the remaining elements would be highly positive.
Okay, so most negative, you mean the minimum sum subarray?
Right. And in fact, minimum sum subarray is kind of a standard problem, isn't it? It's Cadence algorithm can be used to just find out what is the sum of the minimum sum subarray in this array, and that would be big of n. Whatever that sum is, uh, take it out, and the remaining elements they sum up together to send your robot as right as possible. So that is solved.
Got it. And then you can also do it for max, just the same algo.
Exactly. For sending the robot to the left, now I'll find out the max sum subarray, and then I'll remove it, because that subarray was sending my robot to the right. So throw it out. Throw that subarray out.
Okay. Some subarray is found in again order n, and then you take these two subarrays, throw them out.
Yeah, the upper one gives me how much right can I send my robot to. The lower part gives me how much left I can send him to.
Awesome. So Karthik, this works, but this is just part one of the problem. The real problem is this: you can remove a subarray, yes, but you cannot remove any subarray that you like. Basically, the subarray has to have the same number of left and right instructions. So
Okay.
frequency of left instructions has to be equal to frequency of right instructions in the subarray that you remove.
Oh, okay. I liked the problem earlier.
But this is interesting because initially, I mean, this is a standard algorithm. This seems to work, but can you maybe modify this algorithm, or do you need to totally think of a different approach? Is the question.
Okay. So since the entire problem has changed, let me think. I think Ncube still works with a few modifications here and there.
Yes, Ncube definitely works. Yes.
Simply discard those subarrays which are not valid. By valid, I mean the ones that you are allowing me to remove, basically with same frequency of L and R.
So okay, this is the worst case time complexity.
Still works.
Yeah. What about n square with prefix sums? Can you still do something about it?
With prefix sums, I think I can. But what I need to do is, right, it will still work. I'll just discard those subarrays which are not good or not valid. Simply discard them.
Okay, I'm kind of understanding what you're saying. you want to find out in this subarray whether it is a valid subarray or not, depending on how many left and right instructions have existed in this.
Exactly.
Okay, so -1, 0, +1, -1 gives us it gives us 0 again. So
the idea here is that the net positive seen till I and the net positive seen till j minus 1. See, in the subarray j to I, if it is valid, the count of positive and the count of negatives add up to give me 0.
yeah,
Right. So that means whatever was the net positive I had seen till j minus 1, that would stay at I also.
and that makes total sense. Basically, you're saying that, look, if I got a -1 over here, and then someday later I got another -1, how is this even possible? The only way this is possible is that these guys did nothing
Right.
to the
Exactly.
overall sum.
Exactly.
Right. Okay. So you're going on taking the sum, the overall sum. When you get a number x. If the only way that you're going to get x again is if the total number of lefts, the total number of positive instructions is equal to the total number of negative instructions. You're saying that this is then a valid subarray.
Exactly. Like you can write it like this. Whatever is the net positive seen from 0 till j minus 1, if you add the net positive in the region j to I, okay, this should be equal to the net positive seen from 0 till I. Does that make sense?
Yes, it does make sense. It does make sense. Yes.
Right. And then for j comma I to be valid, what you would like is that the net positive seen in the region j to I should be 0.
Correct. So if this is 0,
so that automatically says that okay, this and this should be equal.
Yeah, so basically in a prefix 0, I mean this can be removed, right? Because that's what we are doing here.
Right. Basically, we don't need to keep track of 0. This was only to illustrate the formula.
Okay, yes, that makes sense. Okay, so order n square is now done. This is good. Can you do better?
Okay, so assume that there is a subarray from j to I and it is valid to remove it.
So you want to remove this subarray from j to I?
Yeah, let's say I am allowed to do it. That means NPS of I would definitely be equal to NPS of j minus 1.
Got it. So this is a valid subarray, and you are now getting the sum over from these two sums.
Right. So like it would be capital S, which is the sum of all the elements, minus the removed portion.
Okay, so that's not too hard. Capital S minus sum of j comma I. So that is basically capital S minus, if you have the prefix sum, so prefix of I minus prefix of j minus 1. Yeah, that's a plus here.
Yeah, exactly. So I think that makes perfect sense. And when I'm at the ith index, I would want to remove the subarray starting from some valid j till I that is as negative as possible.
Yes. So the idea is you have many candidate j's for every I, and you want to find the one which gives you the biggest payoff.
Right.
This array, now let us say that I exists here and you have many possible j's. What is the best place to jump is what you're looking for, right?
Okay. Right. Currently in the brute force, you will jump into all of these valid ones.
Yeah, currently you might have n positions. That's why, I mean, whatever, n by 4, whatever. So that's why it is order n square. Let's understand this with the help of an example. Let's take the example of 50, 20, minus 15, minus 30, and 7. So if we take the prefix sums of this array, we are going to get something like 50, 70. Yep, we are just adding these two numbers here. So that is 70. This is 55. We then have 25. And finally we have 32 with these two numbers. The other thing that we are interested in is the direction of these movements. So the other thing that we are interested in is the direction of this movement. So all we need to do is just look at the sign of this movement and then write down the direction. So over here it's a positive one, so +1. We have another positive sign here which makes it +1. This is -1, and then another -1 before you get a +1. So the brute force approach is quite simple. All we need to do is iterate over the array. Let's say I goes from 0 to 1 to 2 and so on, and at every position it sees behind for a particular j, right? Can I create a subarray from I to j? So I is here, and then you have possible j values going behind. So j is here. That tells you that because it goes from 0 to n minus 1, there are n possible positions here, and up to j, which is, you know, effectively the total number of subarrays that you have. So that is n square subarrays. For each subarray, what we are doing is we are taking the prefix sum up to I and subtracting the prefix sum up to j minus 1. This is giving us the sum of the subarray that we are dealing with, and if that sum is large, then we are happy. But because of this additional constraint of the number of lefts and rights that you have in the subarray should be equal, what we effectively did is take a prefix for the directions also. Okay, and why did we do this? If you take the prefix of the directions, we get +1, +2, -1 makes it +1 again, and then you have another minus which makes it 0, and then you have +1 which makes it +1 here. Okay, and there is another thing which is effective in all prefix sum arrays, which is at index number -1 or at an empty array, you have the prefix sum as 0. So over here again you have 0. Now here's the interesting bit. If we want to find what is a valid subarray, which arrays have the same number of lefts and rights, what we need to do is we need to find this direction subarray having a total sum of 0, right? Because the number of lefts you take makes it -1, the number of rights you take makes it +1. So left into -1 plus right into +1, this should be equal to 0, and the only way to do that is L minus R is equal to 0, so L is equal to R. Okay, and how do you find that in a direction array normally? Through brute force, which is going to take you order n. So that will be order n square into n, but we don't want that. So can we do it faster? Yes, through prefix directions. The trick is to look at this element in the cumulative array for directions. +1 occurs here, +1 also occurs here, and it occurs here. What does it mean for a +1 to occur multiple times? The only time that this is possible is that if the sum of elements in between them is 0. Okay, so this is one subarray and this is another subarray that I'm talking about. How does this make sense? Look at these two elements. That's +1 and -1. That's equal to 0. The reason being that in a prefix direction sum, what you're effectively doing is you're saying, hey, what's the sum from point 0 to that point j? Well, it's some x. Then you add some numbers, and then at position I you get x again. What does that mean? Well, there was no point taking the sum of all these elements from 0 to I. You could have taken the elements from 0 to j also. So effectively this entire thing has added nothing to the sum here, which means that this prefix sum is equal to 0. Okay, that's the general idea. So, and you can see it very clearly over here actually. You can see that -1 and +1 makes 0 here. We also talked about this array, so that is +1 and -1 again make a 0 here. So that's the reason why +1 occurs here and +1 occurs here again. You can see that this entire array, right, this +1 and this +1 make this entire array have a sum of 0. That becomes obvious when you apply this logic here. And finally, we talked about this element 0 being at the start of every prefix array. Why is this important? Well, have a look at this element 0. There are no duplicates of it until index -1. So what that tells us is that taking all these elements, right, in the original array, if you take all these elements, it is as good as not moving at all. So, and you can see here, +1, +1, -1, -1. They give you a sum of 0. So it does have a duplicate here. Okay, +2 does not have any duplicate in our array, which means that from this point, there is no way to make a valid subarray as per our conditions. All right. So this is where we are at. We are actually pretty close to an answer. We have an order n square algorithm for finding out all possible i's and j's. But when we are taking j, we are no longer finding all possible j's. We are actually taking only those having the same prefix direction sum as I does. So n into something, in which we are saying prefix direction of I has to be equal to prefix direction of j. Okay, that is the if condition. Initially, the brute force, of course, approach is going to be slow. If we go behind in j one by one, then it's going to be an order n operation, which is not great. So what we can do is start storing these prefix dir up to a particular point. So what I mean by that, take this prefix direction array, take the sum 0. How many positions actually have this sum? Okay, position number -1. Okay, that is basically an empty array. Then you also have position number 0, 1, 2, 3. These are the positions which have a sum of 0 in the prefix direction sum. Now take +1. +1 has positions of 0, 2, and this number, which is 4, right? Finally, we also have another one, +2, which has a single position of 1. So what can we infer from here? We can tell that +2 can never be created because every array needs 2 points. This has a single point, so there's nothing to do. +1 can be created in how many ways? You need a start and an end position. So you have 3 possible start positions. And for the first start position, you have 2 possibilities. For the second start position, you have, this is over here, you have 1 possibility. And for the third start position, you have no possibilities. So effectively, the total number of arrays that you can create here is equal to n into n-1 by 2. In this case, you are avoiding a lot of wasteful computation. Like if you get a prefix sum at this point of +2, then you don't need to try every possible subarray with j decrementing 1 by 1. You just see in +2 there is no other corresponding index, so you just don't do any computations. In +1 you do just 3 computations. You go back to these 3 positions and check whether you can create a valid subarray, and then you check what is the sum of the array that you're creating, right? Using this formula, you'll be able to say whether this is maximized or not. So we have saved on a lot of computations, but it is still not enough. Reason being that you might get especially unlucky. Let's say you have the directions of the robot as +1, -1, +1, -1, and +1. Okay, so all you're doing is alternating. You're either going to the right, and then the next movement you're going left, and again you're going right. So the cumulative sum array is going to be 1. You have 0, then you have 1, you have another 0, and you have 1. So this map that we are creating to avoid a lot of computation on every I. So at I, if your sum was +2, then you were just checking this person. But now in your I, you can have just the sum of 0 here and here in 2 positions, and 1 here, here, and here in 3 positions. Actually 0 again occurs over here, so yeah, that will also be in 3 positions. If this is of size n, then effectively at every I you are checking for n by 2 positions possible. For every I n, you're doing n by 2 computations at least, which is order n square. Okay, so this is still, I mean, it's an improvement. It's definitely a constant time improvement, but it is still slow. Okay, so how do we reduce the comparisons that we are having here for every I? How many j's we need to compare with defines our time complexity. Currently it is order n square. What we can do is we can instead look at what our objective is. Our objective is to take the entire array and find a subarray such that we can subtract this part out, right? Once we eliminate this part of the subarray, we'll be left with two subarrays, one on the start and one on the end, and their cumulative sum is what we want to maximize or minimize. That's, we want to send the robot as much possible to the left or as much possible to the right. This is the basic idea. We want to get rid of the subarray. Okay. Now that we have defined this, what is exactly this sum? So let's take the total subarray sum to be capital S. Let's take this subarray sum to be clearly subarray of I to j, right? What is that? That is equal to S minus, if we define this as a prefix sum, we have 0 to j minus 1 and 0 to I, right? So I'll just write that down for prefix sum minus 0 to I, but you also need to do a plus prefix sum from 0 to j minus 1. What does this part of the equation tell us? For every I, we are searching for corresponding j. So for every I, effectively the prefix sum up to I is constant, right? For every constant I, this entire part is constant. It's only that the prefix sum of j minus 1 is changing. So putting that in a for loop, let's say int I equal to 0 to n minus 1, effectively we'll be having only this component changing, right? And we are trying to maximize this part or minimize this part. Like we said, we are trying to get an extreme value, a maxima or a minima. So let's say maximum. What happens then? Well, the more positive this sum is, the more maximum it's going to get. So effectively what we are doing is we are just trying to maximize or minimize prefix of this part, j minus 1. That's what we are trying to do in this entire portion. In the inner for loop, where we go from j equal to I minus 1 to 0, we are just trying to maximize prefix of j minus 1. Okay, now we are very close to the answer, but I'll need your full attention because this does get a little tricky in terms of logic, not so much mathematics, but logic. Okay, so let's take this example. The basic idea, of course, is that at any position I, we are trying to find a j such that we have a valid array. We already defined that a valid array is an array where the prefix of directions up till a position I is equal to the prefix of directions up till a position j minus 1, right? If you have x over here and you have x over here, that's the only time when the subarray over here is giving you 0 in terms of directions. So the total number of lefts will be equal to rights only when this condition occurs. Okay, that's one thing that we have to keep in mind. All right, so if this condition happens, how can we do this quickly? How do we do this in order one time, basically skipping a lot of j's? Well, what we wanted to do is we wanted to store all this stuff in a hash map. So you know this by just going to the position I, prefix of direction. So in your hash map, you'll search the key prefix of direction I. Okay, that is the key. And the values that you'll get are multiple indexes, which was the problem. That's why we are order n square. But now we don't need to store multiple indexes. And why is that? Well, look at this component, right? For every I, we are just going backwards and seeing which has the maximum prefix j minus 1. And we are choosing that. So two things are happening. Firstly, we are checking if the prefix direction sum is matching that at I. Okay, so we are going to the key and then we are taking the maximum possible value for that key. Okay, let's take an example so that things are a little more clear. Let's take this component, right? At this point, what is going to happen? With our earlier algorithm, we were going to store two positions, here and here. Now I'm claiming that we don't need to store both positions. Instead, we can look at what is the prefix sum of this array. So instead of storing the indexes, I can instead store what the prefix sums are, right? I said 0 and 2. So instead of storing 0, I'm going to see up to this index, what is the prefix of j minus 1? Prefix of j minus 1 till this point will be 0. And index number 2. So come here. What is prefix up of j minus 1? Prefix of j minus 1 is 70. So that is 70. Now I want to maximize, right? So if I want to maximize the prefix of j minus 1, I don't need to store 0. I just need to keep the maximum value of 70. And at every point, I'm not going to be storing all possible indexes. I'm just going to be storing the maximum possible value that I can encounter because this is the only value that I care about for a given prefix direction key. Okay, take your time to understand this. The basic idea is that from every point I, we are concerned only about a few positions which are valid arrays, right? Those valid arrays are defined by this condition. So we used a hash map to sort that condition. The other thing is that for a given valid array, we are only concerned about that prefix sum which removes the maximum or the minimum. And how will you update this value? Like, how is this value getting updated? Well, over here, what will happen is you'll see 35 is the answer, but actually j minus 1. So we need 25. So you see to maximize amongst 70 and 25, which value is greater. So if you're trying to maximize, then 70 is larger, and you'll keep this value. You'll ignore this 35 value. So even if you had a larger array, the later values having the same prefix sum of direction of 1, let's say this would go to 0 and then come back to 1. At this point, you would just see 70 instead of seeing 35 also as a potential value, because you're just storing the max. So this solves the problem. The basic idea here is that you want to go as far right as possible or as far left as possible, which means you want to maximize this as much as possible or minimize this as much as possible according to the equation, whether this is max or min. You have to try both, and eventually the largest possible difference that you can get, the largest possible negative or positive number you can get from S is what you want to accept. So this was a pretty involved problem. I think Karthik did exceptionally well. He actually had solved this problem in real time, but the explanation took me a lot of time to understand. So that's why I have actually condensed this. I'm sorry for going away from the live format. If you like the video, then be sure to hit the like button. Karthik is also having a YouTube channel which is excellent for algorithms and for competitive programming. So if you like competitive programming or algorithms, be sure to subscribe to his channel also. And there's also interesting links for interview ready in the description below. Wishing you all the best, guys. Take care. See you.